Hello friends, I welcome you in lecture number 14 on nonlinear partial differential equations of first order. In today's lecture we are going to discuss some more examples on Charpit's method. So let's start with example number 1. Find complete integral of p square x plus q square y equal to z. So the first step in Charpit's method is to rewrite given equation in such a way that all the non-zero terms are on one side. So we rewrite given equation as p square x plus q square y minus z equal to 0, and we give this number 1. Then we assume that left hand side is denoted by small f, which is a function of x, y, z, p and q. So suppose p square x plus q square y minus z equal to f. Then we require partial derivatives of f. So if we differentiate f partially with respect to x, there is no x here, so derivative of these two terms is 0, and derivative with respect to x of first term is p square as it is, derivative of x is 1. Similarly, del f by del y is q square as it is, derivative of y is 1. Partial derivative with respect to z is minus 1. Partial derivative with respect to p. So here x is constant, derivative of p square is 2p, so it is 2px. And partial derivative with respect to q is 2qy. So once we have partial derivatives, we can write Charpit's auxiliary equations. So Charpit's equations or auxiliary equations are, now we know what are the Charpit's equations. Dx upon del f by del p equal to dy divided by del f by del q, which is equal to dz divided by p into small fp small q into del f by del q, dp divided by minus fx minus p into fz, and the last fraction is dq divided by minus fy minus qfz. So you have to remember this Charpit's auxiliary equations. Now we substitute values of these partial derivatives in these equations. So here del f by del p is 2px. So therefore del f by del p is 2px. Del f by del q is 2qy. dz divided by p into 2px. Here we have p into del f by del p, that is p into 2px, which is 2p square x, plus q into del f by del q, that is 2q square y. This is equal to dp divided by minus del f by del x, so which is minus p square, minus p into del f by del z. Del f by del z is minus 1, so minus p into minus 1 will be plus p. Similarly, dq divided by del f by del y, which is q square, and here we have minus del f by del y, so we write minus q square. Del f by del z is minus 1, so minus q into minus 1 is q. So we give this as number 1. These are the Charpit's equations. Now from these 5 fractions in equation number 1, we have to identify 2 fractions such that we are able to decide values of either small p or small q. So if you concentrate on fraction 1 and fraction 4, then it is possible that we may combine these two fractions and we may be able to find out value of small p. But if you go in that way, it is going to be very lengthy. So here I am not going in that way. Similarly, if you wish, you can combine this second fraction with last fraction and you can try to find out small q. But here we are not going in that way. What we are doing is we are generating new fractions by selecting proper multipliers. So we will generate one fraction by using these two fractions dx and dp. So how to select proper multipliers? So here you can see, here we have minus p square and here I have 2px. So if I multiply 2px by p square, then I will have 2 times p cube x. And if I multiply this whole fraction by 2px, then I will have minus 2p cube x plus 2p square x. And if we add these two, this 2p cube x will cancel out and we will be left with 2p square x. So that will be our new generated fraction, p square dx plus 2px dp divided by 2p square x. Similarly, we will multiply this by q square and this by 2qy and we will generate another fraction, and then we will combine those two generated fractions to obtain value of small p or small q. So what we are doing, we are generating new fractions by selecting proper multipliers. So each fraction in 1 equal to, so first I select this 2 dx and dp. I multiply d square this by p square and I multiply this fraction by 2px. So in the numerator I will have dx is multiplied with p square and dp is multiplied with 2px, and here also 2px is multiplied with p square and 2px is multiplied with denominator of dp, which is minus p square plus p. So this is new fraction generated by selecting multipliers. P square is multiplied with first fraction, 2px is multiplied with 4 fractions and remaining fractions are multiplied with 0. Similarly, we generate another fraction by multiplying this second fraction by q square and last fraction by 2qy. So that new generated fraction will also be equal to each fraction and this new generated fraction. So another fraction which we will generate is dy is multiplied with q square and dq is multiplied with 2qy and denominator of dy, which is 2qy. So 2qy is multiplied with q square and here instead of 2px we have 2qy. 2qy is multiplied with minus q square plus q. So as we know, if we generate new fractions by selecting multipliers in this way, then that new generated fractions are also equal to each other. Now we simplify these fractions and then we try to find out the solution. This I write as it is, and here as we discuss, or we can write one more step, 2p cube x minus 2p cube x plus 2p square x. This equals q square dy plus 2qy dq. This is 2q cube y minus 2 cube of q into y plus 2q square y. So we can see these two will cancel out and we are left with 2p square x. So p square dx plus 2px dp divided by 2p square x. Here q square dy plus 2qy dq divided by 2q square y, and 2 will cancel out. So here we are left with p square x and here we are left with q square y. Now if you observe this numerator, then it is nothing but total differential of p square into x. This I can replace by differential of p square into x. Differential of p square into x equal to p square as it is dx plus x as it is 2p dp. Similarly here also we have differential of q square into y. Okay. Q square as it is differential of y plus y as it is differential of q square is 2q dq. Okay, so now we can see this is separable, so we can integrate both sides. Integrating we get, so integral on left hand side is log of p square x equal to log of q square y plus log a, where a is arbitrary constant. So this we can rewrite as log p square x equal to log, using property of logarithm, this is a into q square into y, and because log is 1 function, this implies p square into x equal to a into q square into y. So this is the relationship which involves p and q. Now if you observe equation number 1, then here we have p square into x. So we will put p square into x equal to a into q square into y, and let's see what happens. Put or using equation number 3 in equation 1. Using 3 in 1, we have equation 1 is p square into x, so we put p square equal to a into q square y. Given equation is p square into x, so this is replaced by a into q square y, and plus q square y minus z equal to 0. So here we write plus q square y minus z, which is 0. So from this we can obtain value of small q. Here we take q square common from these two terms, or we can take q square y common. So we have a plus 1, this z I take on right hand side. So finally I obtain q square equal to z divided by y into a plus 1, and therefore q is square root of z divided by y into a plus 1. So this is nothing but small q. Now using small q we can obtain p square, or we can obtain small p using equation 3. So we can give this number 4, and from 3 we can write p square equal to a q square y by x. From 3 p square equal to a times q square y divided by x. Let me check again. Okay, from this I obtain p square equal to a q square y divided by x, and q square we can replace by z upon y into a plus 1. So here I replace q square by z divided by a plus 1. So therefore p square is nothing but ayz divided by x into a plus 1. Q square is z upon y into a plus 1. I made a mistake here. Here I have to write z upon y into a plus 1. So this y will cancel out, and we are left with a into z divided by x into a plus 1. So therefore small p is nothing but under root of az divided by x into a plus 1. So now we give this number 4 or 5. So we have now values of small p and small q. So now we put values of p and q in dz equal to p dx plus q dy. So we know that dz is nothing but p dx plus q dy. So here I substitute values of p and q. Putting values of p and q from 4 and 5, we get dz equals p is under root az upon x into a plus 1, under root of az upon x times a plus 1. So p times dx plus q, value of q is square root of z upon y into a plus 1. Square root of z upon y into a plus 1 dy. Let me check again. Value of small q is z upon y into a plus 1 in the square root, and value of small p is az upon x into a plus 1. So this we can rewrite as, now here we have square root of z and a plus 1, so that we can take common. We can rewrite this as under root z upon this, we can take outside, and here we are left with under root a upon under root x dx, z upon a plus 1 outside, under root a divided by under root x dx, plus here we are left with 1 divided by under root y dy. Square root of z upon a plus 1 is common, and this we have to transfer on left hand side with dz. So we have square root of a plus 1 divided by square root of z dz. This is square root of a divided by square root of x dx. Okay, we keep this as it is. Now this is easy to integrate. or we can write one more step. We can rewrite 1 upon under root z as z to the power minus 1 by 2. Same thing here, x to the power minus 1 by 2 dx plus y to the power minus 1 by 2 dy. So now we are able to integrate. It is easy to integrate. Integrating, left hand side is under root a plus 1 z raised to minus 1 by 2 plus 1, which is 1 by 2. So z to the power minus 1 by 2 plus 1 divided by 1 by 2. Same thing here, x to the power minus 1 by 2 plus 1 divided by 1 by 2, and y to the power minus 1 by 2 plus 1, which is 1 by 2 divided by 1 by 2, and constant of integration I adjust as b divided by 1/2 because I am having 1/2 in each term, so that I can cancel out 1/2 in the next term from each term, and this I rewrite as square root of z. This is square root of x plus square root of y plus square root of b. So this is required complete integral, which is complete integral of given equation where this small a and b are arbitrary constants. So this is one more example of Charpit's method, in which the new thing is we are not comparing fractions directly, but what we are doing, we are generating new fractions and we compare those generated fractions to find out values of small p and small q. We consider one more problem of this type. Find complete integral of z square equal to pqxy. So the first step is we rewrite given equation is z square minus pqxy equal to 0, and we give this number 1. Then we denote this function, left hand side is denoted by small f, z square minus pqxy is denoted by small f. Then we write down all the partial derivatives. Partial derivative with respect to x is minus pqy. Here minus pqy is constant, derivative of x is 1. Similarly, del f by del y is minus pqx, del f by del z is 2z. Partial derivative with respect to p is minus qxy is constant, derivative of p is 1, and del f by del q is minus pxy is constant, derivative of q with respect to q is 1. Now next step is write down Charpit's equations. So Charpit's auxiliary equations are dx divided by del f by del p equal to dy divided by del f by del q, dz divided by p into del f by del p plus q into del f by del q, dp divided by minus fx minus p fz, dq divided by minus fy minus q into fz, and then substitute values of derivatives in these equations. Del f by del p is minus qxy, so here we write minus qxy. Del f by del q is minus pxy, So here we write minus pxy. Here this is multiplied with p, so we have minus pqxy, and this is multiplied with q, so again we have minus pqxy dp divided by minus del f by del x. So del f by del x is minus pqy, so minus del f by del x is pqy. So here I write pqy minus p into del f by del z. So del f by del z is 2z and it is multiplied with p. So we have minus 2pz. And this is the last fraction dq. What is del f by del y? It is minus pqx, but here we have minus del f by del y. So we write plus pqx minus q into del f by del z, which is 2z. So we have minus 2qz. Now this I can rewrite as minus 2 times pqxy. So this is nothing but minus 2 times pqxy. Now here also we are not able to compare the fractions directly. You can see if I try to compare these two fractions which contain dx and dp, then I have other variables are also present. So I cannot compare fractions directly to find out the values of small p and q. So what I will do here is I will multiply this fraction by small p, and this fraction will be multiplied by small x. So if I multiply this by small p, I will have minus pqxy here, and if I multiply this by small x, I will have pqxy. So that will cancel out pqxy. So this will be multiplied with small p, and this fraction will be multiplied with small x, and other fractions will be multiplied with 0, and we will obtain new generated fractions whose numerator will be p dx plus x dp. Similarly, we will multiply this by q, and this last fraction will be multiplied with y. So here also pqxy will cancel out, and the numerator of generated fraction will be q dy plus y dq, and then we will compare those two new generated fractions. So in this way we can write directly each fraction in 1 equals each fraction in 1 equals 2. So here if we consider first and fourth one, we have numerator as p into dx plus x into dp. P into dx plus x into dp, and let's write denominator p into dx. So here we multiply with p, so we obtain minus pqxy, and numerator of dp is multiplied with x. So this is multiplied with x, so we have pqxy minus 2pxz. Pqxy minus 2pxz, and another generated fraction is dy is multiplied with q, and dq is multiplied with y. It is symmetrical to this, so I can directly write down. I will have pqxy instead of 2pxz, I will have 2qyz. Okay, you can check here. this is multiplied with q, so we have minus pqxy. This is multiplied with y, so pqxy minus 2qyz, which I have written here. Now this 2 will cancel out, here also this 2 will cancel out, so we left with p dx plus x dp divided by minus 2pxz. This is equal to q dy plus y dq divided by minus 2qyz. Now here you can see z and minus 2 will cancel out, and we are left with p into x. In the denominator of both sides we cancel out minus 2z, and if you observe, this is nothing but total differential of p into x. If we take total differential of p into x, then it is p into dx plus x into dp. Similarly, this is nothing but total differential of q into y. We can observe differential of q into y is q as it is dy plus y as it is dq. So now we can integrate directly to obtain the relationship between p and q. So integrating, we have log px equal to log qy plus log a. This, using the property of logarithm, I write as q into a into y. And because log is 1 function, I obtain p into x equal to q into a into y. So this is the relationship between p and q. Okay, we give this number 3. So I have p into x equal to q a y, which I can use in given equation. So I have p into x equal to q a y. So given equation is z square minus pqxy equal to 0. Equation 1 is z square minus pqxy equal to 0. This I can rewrite as z square minus qy into px equal to 0. And here we replace px by qay using 3. So therefore z square minus qy, px is multiplied by qay equal to 0. So we are using number 3 here, p into x equal to qay. So from this I will be able to find out value of small q. This is nothing but q into q, q square, y into y, y square, and this is small a. So it is better we may write log a square here. Constant of integration can be adjusted as we wish. So to avoid square roots, we replace this by a square. Okay, so here I write a square. Here also I write a square. So q square, y square, a square equal to 0. And from this I obtain q square, y square, this is square, a square equal to z square. And this will give me the value of q square as z square upon y square into a square. And therefore taking positive square root, we obtain q equal to z divided by a into y. So we are able to find out small q. Now small p is, from equation 3, small p is q a square y divided by x by 3. small p is q a square y divided by x. So let me check again. P equal to q a square y divided by x. So here we substitute value of small q, which is z upon ay. Q is replaced by z upon ay into a square y divided by x. So therefore we can see here we will have a into z. Y will cancel out, 1a will cancel out. So a into y will cancel out and we are left with p equal to az by x. So we now have values of small p and small q. So the last step is write dz equal to p dx plus q dy, and then we substitute values of p and q. P is az by x dx, q is z upon ay dy. And this z we can take on left hand side by taking common. So we have 1 by z dz equal to a by x dx plus 1 upon ay dy. Okay, so you can see we have taken this z common from both the terms and we are transferring it to the left hand side. So we can see this is separable. So if we integrating, we obtain log z equal to a log x plus 1 by a log y plus constant of integration we write as log b. Now this we can rewrite as log z equal to log of x raised to a plus log of y raised to 1 by a plus log b, using property of logarithmic function. So therefore log z is again log of x raised to a into y raised to 1 by a into b. And because log is 1 function, we obtain z equal to x raised to a y raised to 1 by a small b. So this is our complete integral. So which is complete integral of given equation 1, where a and b are arbitrary constants. So now I hope it is clear how to solve nonlinear partial differential equations of first order by Charpit's method. I hope you like my lecture. If you are new on this channel, please subscribe my channel for upcoming lectures of each mathematics subject of engineering. Thank you very much.